Hey everybody. Before we talk any more about antiderivatives, I need to talk about something called differentials. This will be a very brief coverage of differentials, and our emphasis is going to be on computation and not theory. But remember, if y equals f of x, then dy dx and f prime of x are both notations for the derivative. And the dy dx notation comes from the fact that the derivative is the slope of the line tangent to the graph of f of x. And the slope of a line, maybe I better underline that, the slope of a line represented by m is y2 minus y1 over x2 minus x1. In other words, the change in y over the change in x. And the slope of the tangent is the limit of this. Delta y over delta x is delta x goes to 0. And we represent the quotient delta y over delta x as delta x goes to 0 is dy over dx. Now I want to comment on dy and dx individually. We define dx to be the differential of x. That's what we call it. And dx and delta x are the same thing. So the differential dx represents the change in x. With y being a function of x, the differential of y is a little bit different. dy, well, wouldn't it be nice if I actually defined what d was or gave it a name? Okay. Maybe I better start all over with dy. dy is approximately delta y, and dy represents the approximate change in y given a change in x of delta x. And we call dy the differential of y with respect to x. Now, if you're not getting all of that, don't worry. Here's the point. Thus, we can actually regard dy dx as an actual quotient. And if we can regard dy dx as an actual quotient, then the equation dy dx equals f prime of x can be rewritten as dy equals f prime of x dx. Well, how did we get from here to here? It looks like we just multiplied both sides by dx. And that's what we did. And this is strictly a computational move. Our goal was to compute dy, and we took this equation and multiplied both sides by dx, viewing dy dx as a formal quotient. So let's do a few exercises, just computational exercises, because our interest in differentials is purely computational. Our first example, y equals 3x to the fifth minus 9x. Compute dy, the differential of y. And in case we're wondering, yes, this is our f of x. So, how do we compute dy dx? Or how do we compute dy? First of all, we need dy dx. So we compute the derivative of both sides with respect to x. So we have dy dx equals f prime of x, 15x to the fourth minus 9. And what do we do next if we're looking for dy? If you're hesitating but you're thinking multiply both sides by dx, you're right. Dy is 15x to the fourth minus 9 dx. And it's that simple. Here's dy. This is what we wanted to compute. And we computed it. Well, that was too easy, wasn't it? Let's do another one, okay? Another example just to make sure we got it. Y equals sine of x. So sine of x is our f of x. We want dy, the differential of y. So remember what we did before. Compute the derivative of both sides with respect to x. So that's going to give us dy dx equals cosine of x. We have dy dx, and what is it we're looking for? We're looking for dy, aren't we? So we just multiply both sides by dx. Dy equals cosine of x dx. And it's that simple. It is that simple. But remember, we're not trying to get into theory here. Our interest in the differential is purely computational. Now let's do another one. Maybe just because we can't believe even still that it's that simple. Y equals secant x. Compute dy, the differential of y. We'll compute the derivative of both sides with respect to x. And we get secant of x, tangent of x. We have dy dx. We want dy, so what do? Multiply both sides by dx. And that gives us dy is secant of x, tangent of x, dx. Now I'll change things up a little bit, just a little bit. I'm not going to call this y. I'm going to call it u. Let's say we have u equals 10x cubed, and we want to compute du, the differential of u. Well, is anything really going to change here except the name of the variable? No. Everything else is going to be the same. We want du, so we compute the derivative of both sides with respect to x. And this gives us du dx. Since we want du, we multiply both sides by the differential dx. That's our interest in differentials. Here's what we want to get down. Something called U-substitution. U-substitution is the analog of the chain rule. U-substitution is to integration what the chain rule is to differentiation. And we can also say that U-substitution undoes through integration what the chain rule has done through differentiation. And remember, integration and differentiation are reverse processes. Or if instead of integration we want to say anti-differentiation, that's fine. U-substitution undoes through anti-differentiation what the chain rule has done through differentiation. And remember, anti-differentiation and differentiation are reverse processes. Each of them undoes the other. So let me draw a schematic diagram, or maybe two, of how U-substitution and the chain rule are related. Okay, the chain rule and differentiation versus anti-differentiation and U-substitution. Remember what the chain rule does. The chain rule tells us how to compute the derivative of a composite function. So through differentiation, the chain rule gives us the derivative of a composite function. U-substitution takes the derivative of a composite function and through integration or anti-differentiation gives us back the original composite function plus a constant. Now we can start here with anti-differentiation. What we have here is the derivative of a composite function, and through anti-differentiation or integration, U-substitution takes the derivative of a composite function and gives us back the original composite function plus a constant. And then differentiation and the chain rule take this composite function. And remember, the derivative of a constant is 0. So it takes this composite function, f evaluated at g, and through differentiation, the chain rule gives us derivative of the outer, evaluated at the inner, times derivative of the inner. The point that we want to make is that if we start with the derivative of a composite function and integrate using U-substitution, we get the original composite function. And then if we turn around and differentiate with the chain rule, we get the same derivative of a composite function that we started out with. In this case, the chain rule undoes U-substitution. U-substitution gives us the derivative of a composite function, and it gives us that composite function. The chain rule takes this composite function and gives us the derivative of a composite function that we started with. So here the chain rule, through differentiation, undoes U-substitution and anti-differentiation. And up here, differentiation gives us a composite function. Differentiation takes a composite function, and through the chain rule, it gives us the derivative of a composite function. U-substitution takes that derivative of a composite function and gives us back the original composite function, f of g of x, plus some constant. So U-substitution and the chain rule undo each other. this might seem to be a peculiar thought. Let me introduce it this way. Do we ever have any doubt as to whether or not to use the product rule? For example, would we use the product rule to compute the derivative of this thing? The answer is yes. We look at it and we say it's a product. So we use the product rule when we compute the derivative. Or what about this? X cubed cosine of x. If we wanted to compute the derivative of this function, would we use the product rule? Well, of course we would. This is a product. All right, what about this? Suppose I wanted to compute the derivative of this function. What should we use? And we say the quotient rule, because this is a quotient. Well, okay, what about this? Suppose we want to compute the derivative of this function. What rule should we use? And you answer the quotient rule, because this is a quotient. And the thing is, for products and quotients and so forth, there's never really much of a dilemma trying to figure out what rule to use, because we always know a product when we see it. We always know a quotient when we see it. So we don't have to look at it and say, well, I don't know. I don't know if this is a quotient or not. We look at it and we say, of course it's a quotient. We're going to use the quotient rule when we compute the derivative of this. So up until now, there's never really been much of a dilemma as far as what rule to use when we compute the derivative of a product or of a quotient or of a composite function, because we know what all of those things look like. And so we know the proper rule to use. But situations that require us to use U-substitution are not always that obvious. The only time we use U-substitution is to compute the antiderivatives of expressions that are derivatives of composite functions. So when do we use U-substitution? When we're trying to compute the antiderivative or the integral of something that's the derivative of a composite function. Okay. Well, it's not quite as straightforward. And so what we want to do is make sure that we know exactly what the derivative of a composite function looks like. And that's the point here. We use U-substitution only to integrate or anti-differentiate expressions that are the derivatives of a composite function. So we need to know what the derivative of a composite function looks like. And that's what we're about to do right now. We'll write down a generic composite function. And we have an outer function. We have an inner function. And what do we get? Well, we know what we get because for a few weeks we've been walking around saying to ourselves, derivative of the outer, evaluated at the inner, times the derivative of the inner. Okay, we got it. So derivative of the outer, evaluated at the inner, times derivative of the inner. That's what we have. And I'll even label it. Derivative of the outer, evaluated at the inner, times derivative of the inner. We want to know what derivatives of composite functions look like. So we've taken a generic composite function, we've computed its derivative, and now we're going to analyze this thing. We're going to look at the derivative and pick out any and all unusual characteristics, characteristics that aren't common to all functions in general. And one of the things that we might have noticed is that we start with a composite function, f evaluated at g of x, and the derivative has in it a composite function, f prime evaluated at g of x. F prime is the outer, and g of x is the inner. So the derivative of a composite function itself contains a composite function. So this is one identifying characteristic of expressions that are the derivatives of composite functions. Now we'll look at anything else that we can see here in the derivative that seems to be unusual in the sense that it's not necessarily true of functions in general. And perhaps what gets our attention here is we see g of x here, and we see g prime of x here. And I'm going to refer to this as a function derivative pair. So the derivative of a composite function contains a function derivative pair. So in the derivative of the composite function, we see a function and we see its derivative. That's something that we don't see in all mathematical expressions. So this is definitely a telltale symptom that we're working with the derivative of a composite function. And I'll write something else down too. The function of the function derivative pair and here's the function of the function derivative pair. The function of the function derivative pair is also the inner function of the composite. So those are three good observations to make. And when we are trying to decide whether or not to use U-substitution, we're going to look for these three things. And if we see these three things, we're going to go full steam ahead with U-substitution. Here's a good example to start off with. And let me preface our work by saying we can probably look at this and recognize it as the derivative of a composite function. And so by inspection, we can probably figure out what this antiderivative is. But for the sake of learning a method, for the sake of learning the method of U-substitution, work with me on this. U-substitution is that one thing that if we don't get it down pat and we go to Cal 2, we're going to get squashed. On the other hand, if we learn U-substitution well in this course, it will carry us a long, long way in Cal 2. This is an easy example. We can do this without U-substitution, but the purpose of this example is to teach us a method for using U-substitution. So bear with me. The first thing that we do in general is just determine whether U-substitution is appropriate. We wouldn't want to use the product rule on a quotient, right? And we don't want to use U-substitution on an expression that's not the derivative of a composite function. So we need to know whether U-substitution is appropriate. A, is there a composite function? And the answer is yes. Cosine evaluated at x cubed. And here's the outer, cosine. And here's the inner, x cubed. And our rule of thumb for selecting u is to let u be the inner function. I'll write that down. The rule of thumb in this part is to let u be the inner function. So u is going to be x cubed. Now we'll look at another criterion. Is there a function derivative pair and we look here and we say, you know what? 3x squared is the derivative of x cubed. So the answer is yes. And x cubed is our function. 3x squared is our derivative. And the rule of thumb for criterion B is to let u be the function of the function derivative pair. So for part B, u is going to be the function of the function derivative pair. And that is x cubed. The function of the function derivative pair, is it the same as the inner function of the composite? Well, in this case it is. Here's the function of the function derivative pair. Here's the inner function of the composite. So we answer yes. The answer to all three of these questions is yes, which means that we're definitely working with the derivative of a composite function. The answer to all three of these things is yes. So go ahead with U-substitution. Absolutely. You know what? Before I erase anything, maybe I need to make a remark here. We can phrase this question a different way. Is the function of the function derivative pair the same as the inner function of the composite? Well, notice something. The function of the function derivative pair is what we let u be equal to in criterion B. And the inner function of the composite is what we let u be equal to in part A. So instead of saying, is the function of the function derivative pair the same as the inner function of the composite, what we can ask is, do criteria A and B recommend the same choice of u? And this seems to be a much simpler criterion to use. So from now on, this will be criterion C. From now on, do criteria A and B recommend the same choice of U? From now on, this will be criteria C, or criterion C. Step 1 was to determine whether or not U-substitution is appropriate. And it is. So in step 2, we compute du. And we remember that u is equal to x cubed. So to compute du, the first thing we have to do is compute the derivative of both sides with respect to x. And then since we're looking for du, we multiply both sides by dx. Next step, analyze the integral in terms of u and du. So here's our integral, cosine of x cubed times 3x squared dx equals what? Okay. Now this thing, in terms of u is x cubed, right? So cosine of x cubed is the same thing as cosine of u. So that's what this is. This is cosine of u. And now this thing, 3x squared dx. Do we see this anywhere else on the board? 3x squared dx? If we look around, we might notice that we do. 3x squared dx is du. So in terms of u and du, this integral is cosine of u du. So we've analyzed the integral in terms of u and du. Time for step 4. And think about this. We've gone through a lot of trouble to rewrite the original integral in terms of u. Why go to all the trouble to rewrite this integral in terms of u? And then in step 4, when we integrate, rewrite everything in terms of x and try to integrate that? No. We went through a lot of pain to rewrite this integral in terms of u, and we're going to integrate in terms of u. So we have the integral of cosine of u du. And before I actually integrate this, I'm going to say compare. Compare this with this. What's the only difference between this and this? The name of the variable, right? This is the same exact expression as this, except in terms of a different variable. So what this integral does to x, this integral is going to do in terms of u. Do we know what that integral is, or this antiderivative is in terms of x? The antiderivative of cosine of x is sine of x plus c. Well, mechanically, this integral works exactly the same way. This integral does to u what this integral does to x. So this is going to be sine of u plus c. Excellent, excellent, excellent. Now take a look at that for just a little bit. Take a look. And I'll give you about 5 more seconds. If you want to look longer than that, you can hit the pause button. Okay. And that brings us to the 5th step. We started out in terms of x. We need to finish in terms of x. I mean, that would be like me going to Europe on vacation, and I go to this international restaurant, and since it's an international restaurant, they take American currency. So I pay my bill. My bill is so many euros, I don't know how many, but I'm feeling like a high roller, so I pull out a couple of $100 bills and put it down there. And they come back and they give me my change in euros. And I think, is this good? Now, if I knew what my bill was in US dollars and I paid in US dollars, I'd want my money back in US dollars. If my bill was in terms of US dollars, I paid in US dollars, and I got my change back in euros, I'd say, well, I don't know. Is this right? What do you think? I gave him $200, and this was my bill. No, I should have gotten back $87.23 in American cash. But they give me this stuff in euro. I don't know. What do you think? You think this is about right? See, if I pay in one form of currency and I get my change back in a different form of currency, I don't really know if it's right or not. And similarly, if we start out in terms of x with an integral, and I think it was cosine of x cubed times 3x squared dx. If we start out in terms of x and we get our answer in terms of u, well, wait a minute. X is dollars and u is euros. I don't know. Is this right? What do you think? If we start out in terms of x, we want to finish in terms of x. Now, we know what our answer is in terms of u. Our answer is sine of u plus c. But what is our answer in terms of x? I have to re-express this in terms of x. And to do that, I go back to step number 2. Step number 2 has our international rate of exchange. This tells me that 1 U is equal to x cubed, or 1 euro is equal to x dollars cubed. So this is my rate of exchange right here. This tells me how to go back from euros to dollars or from U to X. So U is the same as X cubed. So sine of U is the same as sine of X cubed. And that's our answer. Now, could we have done this particular exercise without using U-substitution? Absolutely, absolutely, absolutely. But our goal was not to integrate this function or this function. Our goal was to get some practice using the 5-step technique for U-substitution. And for the time being, definitely for the rest of this class, and hopefully for the beginning of Cal 2, we'll use this 5-step method for U-substitution. This 5-step method for U-substitution works as our training wheels. Okay, we've learned how to ride a bicycle 50 feet. We still need the training wheels. Now, when we can ride our bike 5 miles on all kind of terrain and we're secure the whole way, we can take the training wheels off. And similarly, when we get a lot of practice using the 5-step method with U-substitution, we can do some of these steps mentally instead of writing everything down. But for now, we want to do the 5-step method, and I'll tell you why. Especially if we're going on to Cal 2. If we know U-substitution, we are going to get off to a great start in Cal 2. And this will keep us going for quite a ways in Cal 2. If we don't get U-substitution down in Cal 1, we're not going to be able to learn it in Cal 2. Our instructor will assume that we already know how to do it, and they will not bother to show us how to do it. And there are going to be exercises that we won't be able to do, and we won't even know why it is we can't do them. So this is something that we need to learn and learn well right now. If we do, Cal 2 will be fairly simple. If we don't learn this right now, we're going to get squashed if we go into Cal 2. So I think we're going to do a few more examples because this is very important. If appropriate, we are going to use the 5-step method to compute this. Now, I suspect this is a U-substitution exercise, but I got to make sure. First step, if I'm thinking of using U-substitution, first step is to see if it's appropriate. And do you remember what the first characteristic of the derivative of a composite function is that we look for? The derivative of a composite function contains a composite function, doesn't it? Okay, so is there a composite function? What do you think? I'll tell you what I think. I'm going to answer yes. And here's my composite function. And this can be an easy thing to forget, so I'm going to beat it to death here. A function raised to a power is always a composite function. This can be easy to overlook because physically it looks different than all other composite functions. But a function raised to a power, that is a composite function. And this is going to be the outer, the raising of something to the 10th power. And this will be the inner. And you remember our rule of thumb for selecting u? What was it? We let u be the inner function, didn't we? So u equals 4x cubed plus 6x squared. Okay. Now our second criterion, criterion B, what was that? Is there what? A function derivative pair, and I think we see one. Let's see, the derivative of the inner function, 12x squared plus 12, yeah, we got a function derivative pair, all right. So 4x cubed plus 6x squared, that's the function. And 12x squared plus 12x, that's the derivative. Now, what was our criterion for selecting u in part B? We let u be the function of the function derivative pair, right? So that means that u is 4x cubed plus 6x squared. And now we do C. And remember, we revised criterion C. Do criteria A and B suggest the same choice of u? And I'll be a son of a gun, they do. Criterion A says let u equal 4x cubed plus 6x squared. Criterion B says let u equal 4x cubed plus 6x squared. So the answer is yes. The answer to A, B, and C is yes. We go full blast forward with U-substitution. And our second step, what is that? Step 2. Anybody got that? Step 2, compute du. So we start off with our choice of u, 4x cubed plus 6x squared. And we want du, so we compute the derivative of both sides with respect to x. And to get du, we multiply both sides by dx. And I think I'll put all of this in a box because from the last example I remember that step 2 contains my international rate of exchange. And I don't want to forget what that is. Step 3, analyze in terms of u and du. So we write our integral down again. 4x cubed plus 6x squared to the 10th. 12x squared plus 12x. And remember what u is. U is 4x cubed plus 6x squared. And down here we have u raised to the 10th power. This is u raised to the 10th power, u to the 10th. Now I just have to figure out what to do with this mess. Do I see this anywhere on the board? And the answer is yes, I do. I see it right here. This is du. So now we go to step 4. Integrate or anti-differentiate in terms of u. So we have integral of 4x cubed plus 6x squared to the 10th times 12x squared plus 12x dx. Whoops. You know what? In step 3, I should have followed through here. I beg your pardon. This is u to the 10th du. So as part of step 3, I should have written this in terms of u. And now in step 4, I'll take this and integrate it in terms of u. Now before I do, let's compare something. Let's compare this with the analogous statement in terms of x. And again, I ask, what's the only difference between this and this? They're exactly the same thing. It's just that one is written in terms of u and one is written in terms of x. So whatever this does in terms of x, this is going to do in terms of u. And we know what this is. This is just a power rule exercise. Add 1 to the exponent. Divide by the new exponent. Well, this is going to do the same thing to u. Add 1 to the exponent. Divide by the new exponent. Plus c. So here's our answer in terms of u. Now I'll give you a minute or two to look at that. Actually, more like 15 seconds to look at that. Okay. Now time for step 5. Re-express in terms of the original variable So I had the integral of 4x cubed plus 6x squared to the 10th times 12x squared plus 12x dx I did say dx, didn't I? I know what this answer is in terms of u. In terms of u, this is u to the 11th over 11 plus c. But I started out in terms of x, I need to finish in terms of x, which means that I need to replace this u with its equivalent in terms of x. And how do I find that? Step 2, where I compute my du, has the rate of exchange between u and x. 1u is equal to 4x cubed plus 6x squared. So I have u, or 4x cubed plus 6x squared to the 11th over 11 plus c. And that is our solution. By the way, suppose I'm not really sure that I did this correctly. I have an answer, but I'm not absolutely sure that my answer is this integral. How can I check? This is supposed to be the antiderivative of that function, right? Which means that this is the function that we compute the derivative of to get the integrand. So if I ever have my doubt as to whether I've done this correctly or not, one way of checking is just to compute the derivative of my answer and see if I get this thing. 4x cubed plus 6x squared to the 10th times 12x squared plus 12x. If I compute the derivative of this thing and I get this, I know I've done it correctly. Now I have something more to show you in the way of U-substitution. To make sure that our process of U-substitution is as versatile as possible, we want to talk about something called an approximate function derivative pair. And we say that f of x and g of x constitute an approximate function derivative pair exactly when the derivative of f is equal to some constant multiple of g of x. So let's take this as an example. F prime of x is equal to 12x squared plus 12x. So clearly, f and g of x don't form a function derivative pair. The derivative of f of x is not the same as g of x. So f and g of x don't form a function derivative pair. But we can't help but notice that g of x does bear some resemblance to the derivative of f prime. Instead of having x squared plus x, we have 12x squared plus 12x. So this is really 12 times x squared plus x, or 12 times g of x. F and g don't form an exact function derivative pair, but they're only off by a constant multiple. So we can say that f prime of x is equal to 12 times g of x. And the important thing here is that 12 is a constant. We're only off by a constant. This notion is going to be helpful in U-substitution exercises. It's going to enable us to apply U-substitution to a much broader category of integrals or antiderivatives. So let's do another example. Okay, another example. Is U-substitution appropriate? Criterion A looks for a composite function. Do we have a composite function here? Yep. Sine is the outer function. 4x cubed plus 6x squared is the inner function. So here's the inner. Here's the outer. And what's the rule of thumb for criterion A? Let u equal the inner function, right? So u equals 4x cubed plus 6x squared. And we go now to criterion B. We're looking for a function derivative pair. Do we have a function derivative pair? And we have to stop and be honest and say, you know what, we don't. X squared plus x is not the derivative of 4x cubed plus 6x squared. So the answer here is no. No, but we do have an approximate function derivative pair for what it's worth. It may be worth something, it may not. Now, we have two choices at this point. We can either say we don't have a function derivative pair and quit, or we can say we don't have a function derivative pair, but we do have an approximate function derivative pair. Let's just go with it. What have we got to lose? So here's our function derivative pair. 4x cubed plus 6x squared. There's the function. And the derivative is x squared plus x. It's not an exact function derivative pair, but we're only off by a constant. And our criterion is to let u equal the function. So in other words, u equals 4x cubed plus 6x squared. And now part C. Do A and B suggest same choice of u? Well, oddly enough, they do. U equals 4x cubed plus 6x squared. U equals 4x cubed plus 6x squared. So, hoping that it's okay that we only have an approximate function derivative pair, we continue. We go on to step 2. And step 2, compute du. U equals 4x cubed plus 6x squared. Du dx is 12x squared plus 12x. And that implies that du is 12x squared plus 12x dx. And because I only have an approximate function derivative pair and not an exact function derivative pair, I'm going to leave a line blank here after this. I just have a hunch I'm going to need some space here. I don't know why, but I'm going to leave myself a line blank. And now step 3, analyze in terms of u and du. So we have sine of garbage times x squared plus x dx. And we remember that u is 4x cubed plus 6x squared. So down here, this is u. U is the inner function of sine. So this is sine of u. And now all we have to do is figure out what we're going to do with this piece of junk right here. And as we have in previous exercises, we look at this thing and say, do we see this anywhere on the board? And we look around and no, we don't see this anywhere on the board. So then we ask the question, do we see anything that looks kind of like this anywhere on the board? And we say, well, we've got 12x squared plus 12x dx. Now that's not x squared plus x dx. And I ask myself this question. What would I have to do? What would I have to do to both sides of this equation to make the right-hand side look exactly like that? If I just divide both sides by 12, the right-hand side turns into this, right? So I divide both sides by 12, or equivalently, I multiply both sides by 1/12. Cool. So now I know what this thing is in terms of du. It's 1/12 du. I'm going to write that down here. 1/12 du. And then I'm going to rewrite my integral in terms of u and du. I have sine of u times 1/12 du. That's my new integral. So I've done step 3. Step 4, integrate in terms of u. So I have sine of u times 1/12 du. And let me ask you something. Multiplication's commutative, right? So sine of u times 1/12, that's the same thing as 1/12 times sine of u, right? We can just switch the order of those two factors. Got the same thing here. But now I'm noticing this factor of 1/12 in the integrand. And I remember there's a property of antiderivatives that tells me I can take a constant factor of the integrand and move it out in front of the integral sign. So that's what I'm going to do. Oh my goodness. My integral is only in terms of u. So I write myself a little note here. Compare 1/12 the integral of sine of x dx. Whatever we do to sine of x down here, we're going to do to sine of u up here, right? The only thing that's different about this integral from this integral, the name of the variable, that's all. And if I integrate this thing, I write the constant down. And I compute the antiderivative of sine of x, which is negative cosine of x, plus c. Well, that's exactly what I do up here. I write the constant down, and I have negative cosine u plus c, which is equal to negative 1/12 cosine of u plus c. I integrated the son of a gun. So now I can do step 5, re-express in terms of the original variable. So my integral is sine of 4x cubed plus 6x squared times x squared plus x dx. This is my integral. And in terms of u, this is what I get. Negative 1/12 cosine of u plus c. Now all I have to do is rewrite my answer in terms of x. And step 2 has my rate of exchange. U is the same as 4x cubed plus 6x squared. So my answer, 1/12 cosine 4x cubed plus 6x squared plus c. This is it. Son of a gun. We didn't have an exact function derivative pair here. We were off by a constant multiple. We didn't have an exact function derivative pair. We were off by a factor of 12 or by a factor of 1/12, depending on how you look at it. But you know what? Here's why it doesn't matter if we're only off by a constant factor. If we don't have an exact function derivative pair, but we have an approximate function derivative pair, we're only off by a constant factor from having an exact function derivative pair. We can take the constant factor that we're off by, and since it's constant, we can move it to the other side of the integral sign. And therefore, our integral will be of a form that we can integrate. The constant that we're off by, we bring out in front of the integral, so it really has nothing to do with the integral anymore. And this is something that we can integrate. So I guess from now on, in criterion 1b, an approximate function derivative pair will be acceptable. And I'm going to write that down. I'm going to write that down as a main observation. Here's the point, and it's a biggie. From now on, in part 1b, where we're looking for a function derivative pair, it won't be necessary to have an exact function derivative pair. In part 1b, an approximate function derivative pair, where we're only off by a constant multiple, an approximate function derivative pair will suffice. And that means that this opens up an entirely new class of functions that we can integrate using U-substitution.